Imagine drifting to sleep under the glow of a giant blue star while vast clouds of cosmic dust slowly breathe in and out around Orion's belt. Tonight's journey follows Alnilam, the radiant heart of that belt, from its blazing core to the quiet edges of its carved nebula, guiding the mind into deep, weightless rest among the stars. If slow science-based space stories help you relax, please like this video and subscribe to the channel so more long cosmic sleep journeys can gently light up your nights. At the heart of the Orion molecular cloud, one bright core burns through the dim river of gas and dust. Alnilam is a massive blue star whose light reshapes the material around it. From this point, the entire belt region slowly reorganizes around one concentrated source of energy. The star does not sit in a clean vacuum. It rests inside uneven layers of cold gas and drifting dust grains that formed long before its core ignited. These layers are patchy and lumpy. Some regions hold dense knots. Other stretches are thin and veiled. As Alnilam shines, the patchwork begins to glow and fade under steady radiation. In the most direct line from the starlight carves a clean corridor through the haze. Dust grains in that corridor thin out over time. Small particles drift or are pushed aside. The path becomes more transparent. In nearby lanes where material is thicker light cannot escape so easily, it scatters and softens so regions to the side take on a faint washed colour instead of sharp brilliance. A clear physical boundary appears between zones of strong direct glare and calmer diffuse glow. At modest scales around the star, this contrast resembles a bright stone set inside cloudy glass. The surface of the stone gleams with sharp edges. The glass around it carries streaks and swirls that never reach the same intensity. On larger scales across the Orion band, that simple contrast scales up into an entire luminous cavity. Alnilam pours out more energy than many typical stars combined. Its power is immense, but can still be phrased in simple terms. The star radiates roughly several 100,000 times the light of an ordinary yellow star. It is as if one lightning flash is frozen with the strength of a whole field of weaker sparks. That single source becomes a reference point against which every nearby cloud strand must adjust. Denser clumps in the path of the radiation cast long soft shadows into the surrounding material. In those shadows, dust stays cooler and thicker. Filaments of gas thread behind them like the wake behind a partially submerged rock in a slow river. In regions that receive direct radiation particles, heat and drift away from the star. They move outward millimeter-sized grains sliding through the gas over long spans of time. The result is a shallow gradient in density that flows away from the central core. Close in space is cleaner and more emptied out. Farther away, the cloud thickens again and regains its mottled texture. This gentle gradient is not perfectly smooth. It carries ripples where local overdensities resist erosion for a while. Each ripple can act as a temporary shield, preserving pockets of cooler gas behind it. Over time, these pockets may stretch or collapse, but their presence still shapes the soft outlines of the cavity wall. A slow zoom outward shows how this one star alters different scales at once. Within a small radius, light, pressure and heating sculpt arcs and ridges that curl around the bright source. At the scale of the Orion belt, Alnilam helps define a central window where the broader molecular cloud seems less opaque. At the scale of the galactic neighbourhood, the star is one of several intense beacons that pick out the spine of a spiral arm. In that context, the cavity is only a modest dimple in a vast curling lane of gas. A quiet limit appears when intuition tries to follow every single photon and every grain. The scene suggests a clean shape and a simple outline. In reality, the paths of light twist through countless small deflections. Individual grains move with tiny jittering motions in response to radiation and collisions with gas. No direct description can track every detail. The best picture is an average surface, a smoothed shell that hides the restless motions inside. At this level, the mind accepts a layered structure and a gentle gradient instead of a perfect map. That acceptance mirrors the way the cavity itself functions. It is a region where conditions lean toward lower density and higher temperature with clear sightlines. The Orion cloud still presses in from outside. Within that balance, Alnilam continues to act as a bright central heart for the local structure. Closer to the starlight favours shorter wavelengths so the surface glows with a hard blue-white tone. As those photons leave the immediate photosphere, dust grains in the nearby cloud redirect part of the light. Some grains are small compared with the wavelength, they scatter blue light more efficiently than red. Others are larger and tend to soften the light instead of sending it in sharp beams. Together they turn a simple spectrum into a layered field of colour. In some directions, the scattered glow takes on a slightly green cast where blue light mixes with warmer components from deeper dust. In other directions, the star remains an almost pure blue point against darker lanes. A mental image that helps is a glowing ember inside uneven fog. Thin regions show a bright core, thick patches show a dim-tinted halo. Here the ember stands in for a hot star, and the fog marks a cold molecular cloud. The physics stays simple. Light travels and meets particles, then either passes through or is absorbed and re-emitted at lower energy. A boundary appears wherever these fates change smoothly from one pattern to another. On small scales, the boundary wraps close around local knots and filaments. On large scales, it outlines the full cavity in a broad rounded shell. From that shell inward, conditions appear ordered by the star. From that shell outward, the original disorder of the cloud slowly returns and prepares the stage for the wider belt structure to emerge. Across the constellation, 3 aligned points rest against the dim band of the Orion molecular cloud. Alnilam sits in the centre of that line as the brightest and most shaping member of the belt. This simple row on the sky hides a deep structure in distance and dust, and in the way light travels along the line of sight. Space in this region does not behave like a flat drawing on a dome. It stacks and overlaps and folds in front of and behind the middle star. Within a patch of sky, no wider than a fingertip, distances change from nearby neighbourhoods to far reaches of the spiral arm. The mind tends to see the belt as 3 identical bees on one straight string. In reality, each star occupies a different pocket of the galaxy, and Alnilam sits deeper inside the central body of the Orion cloud. From that embedded position, its light must cross a longer stretch of gas and dust before it leaves the region. Along that stretch, tiny grains and molecules act like a soft filter. They remove some colours and scatter others. They let the most energetic light escape with only partial loss. The result is a gentle change in colour and brightness compared with a similar star in cleaner surroundings. Alnilam appears slightly dimmer and more modified than it would in a clear vacuum. One rounded number helps hold this picture steady. The star lies at roughly 2,000 light-years from the solar system. That distance becomes easier to sense when turned into a simple walk. Imagine shrinking the gap between the Sun and its nearest stellar neighbour down to the length of a single step. On that reduced floor, Alnilam would stand hundreds of steps away along the same direction. Each step marks the span between stars in the local group. The belt then stretches across an entire long hallway instead of a tiny patch on a ceiling. On that hallway map, the Orion molecular cloud becomes a corridor with uneven walls made of gas and dust. It carries alcoves and arches and recessed pockets where material is thicker or thinner. The belt marks just one bright section along that corridor where 3 powerful stars happen to line up inside the same narrow angle on the sky. Alnilam illuminates a particular slice of this corridor. Its light falls on clumps and filaments and thin gaps that sit both closer and farther than the star itself. Some dust lies in front of the star and acts as a foreground veil that steals part of the blue light. Other material lies behind it and is lit only after the radiation passes the stellar position and continues outward. In that sense, the belt is not a simple row of luminous points. It is the sharp edge of a 3-dimensional landscape carved by radiation and gravity over long times. A helpful anchor image is a row of paper lanterns hung at different depths inside a misty hall. One lantern burns hotter than the others and fills the mist with strong light, yet the haze in front of it still softens the glow and shifts the colour toward calmer tones. From the far end of the hall, the lanterns look neatly aligned on one string. Between them, drifting sheets of mist and darker patches change the clarity and warmth of each light. A similar pattern unfolds along the Orion belt, where Alnilam acts as the central lantern in a hall without visible walls or floor. On finer scales, small changes in dust density along the line of sight produce gentle gradients around the star. A faint halo appears where scattered light adds to the direct glare and smooths the brightness. Slightly farther out, the halo gives way to dimmer lanes, where the viewing path crosses thicker clumps. These features remain invisible to simple eyesight, yet emerge in long exposure views and careful measurements of brightness across the field. At higher sensitivity, the region no longer resembles three neat stars on a blank canvas. It becomes a layered painting of bright cores and soft outskirts and dim strokes of obscuring material. There is a clear limit to intuition in this scene. The mind can picture lanterns in mist and a hallway of steps. It cannot easily hold the exact positions of all real clouds and clumps and stars spread over such great depths. Observations must therefore rely on indirect methods. They measure colour changes and brightness at different wavelengths and compare them with simple patterns of dust and gas. These measurements reveal average dust content and relative depth, but do not supply one perfect picture of the true three-dimensional arrangement. Instead, models reconstruct likely structures that match the data within known limits of resolution and noise. The result is an informed sketch rather than a precise map. Even this sketch carries a quiet reward. It shows that Alnilam's place in the belt is more than a chance alignment of bright points on the sky. The star occupies a region where the Orion cloud is thick enough to shape its light. The same region is thin enough for a broad glowing cavity to form around it. At small scales near the photosphere, radiation pressure pushes outward. At grand scales along the spiral arm, the belt serves as a recognizable landmark. In both regimes, the combined geometry of distance and dust decides how prominent the star becomes. As Alnilam continues in this phase, its place as the central beacon of the belt remains stable over human timescales. Around it, the deeper cloud keeps drifting and slowly reshaping. The simple straight pattern on the sky always hides a richer interior structure. Later sections will move through that interior in more detail. Beneath the smooth blue point seen from afar, Alnilam hides a complex interior with a tight heart of fire. That hidden heart is a nuclear core where intense pressure fuses hydrogen into helium and sets the energy scale for the whole belt region. The core behaves like a compact furnace pressed into place by gravity from every side. Around it, calmer shells of gas receive that power and slowly transform it into the softer light that filters through the Orion cloud. In a mental cross-section, the star looks like a bright seed surrounded by paler layers that fade outward. At the very centre, gravity gathers matter into a region of remarkable density. At this depth, atoms sit so close together that their motions blend into a single hot fluid. Temperature rises to many millions of degrees, and motion becomes frantic on the smallest scales that physics can describe. Particles rush and collide from every direction, and some collisions push protons close enough for fusion to occur. A single rounded figure keeps the strength of this region clear. Each tiny portion of the core can release more energy than many ordinary stars radiate from their surfaces. The comparison is rough, yet it anchors the idea of a small engine driving a much larger structure. This energy does not stream freely into space from the central volume. Surrounding layers form a thick barrier that traps radiation and forces it to move in very slow steps. Energy leaves the core in the form of high-energy photons. Each photon soon meets an electron or nucleus and is scattered into a new direction while giving up some energy. The process repeats countless times. The original photon identity is lost, yet its energy continues outward as a cascade of softer photons. On a scale that suits the mind, the situation resembles light trying to cross a twisting maze of translucent walls. Each wall stands for a scattering event that redirects the path by a small angle. Over time, the path folds in on itself and lengthens. Only after many deflections does energy reach regions where matter is thin enough for a more direct outward flow. Above the deepest layers, temperature and density drop step by step. That change allows a second transport pattern to appear. In some zones, convection takes over part of the work of carrying heat. Convection is the slow rise of warmer material and the slow fall of cooler material in broad loops. In Alnilam, these loops occur in enormous rolls that span large fractions of the stellar radius. The pattern recalls thick storm clouds turning in great arcs above a landscape, although here, the motion is hidden inside a star and never reaches open sky. In the star, there is no visible surface where such motion can be seen directly. The churning remains buried under the outer layers and can only be inferred from changes in brightness and from models of how energy prefers to travel under given conditions. A gentle scale shift helps place these nested processes in context. Very close to the core, small changes in radius bring dramatic shifts in temperature and pressure. A short step inward or outward transforms the rate at which fusion occurs. Farther from the centre, the same radial step brings only modest changes and allows smoother structures like convection cells to persist. Moving out to the full stellar radius, the interior complexity merges into a single stable surface brightness that appears quiet when viewed from the Orion cloud. The contrast between inner restlessness and outer calm becomes one of the defining features of massive stars like Alnilam. There is a firm limit, however, on how directly this interior can be known. No light escapes from the core without being reprocessed. No material can travel from the central region to empty space while carrying an intact record of its journey. Knowledge must come from indirect traces. Measurements of surface colour, total luminosity and subtle pulsations in the outer layers provide constraints. Theoretical models then adjust internal profiles of pressure, temperature and composition until the predicted outer behaviour matches what is seen. These models rely on well-tested nuclear reactions and on basic laws of gas and radiation. Even so, small uncertainties remain about detailed flows and fine-scale structures that current methods cannot resolve. The picture of sharp boundaries and smooth layers is therefore an efficient summary rather than a fully detailed map. In spite of these limits, the broad structure of the core and its envelopes is secure enough to explain the star's influence on its surroundings. A stable, powerful core tends to sustain a high and fairly steady luminosity over the main part of the stellar life. That steadiness matters for the Orion molecular cloud. It means that the gas cavity around Alnilam grows under a roughly constant push, instead of repeated violent pulses. Close to the star, radiation pressure and stellar wind draw out arcs and gradients in the nearby gas. At larger distances, the same constant output keeps the central belt star bright enough to define the line across the sky. The nuclear engine therefore connects two extreme regimes. At one end, crowded particles inside a small core trade energy in conditions that defy everyday intuition. At the other end, faint green-tinted dust, many light years away, glows with light that began as restless photons inside that compact heart. Between those ends lies the full depth of the star, where energy spends long ages moving outward, before it finally steps into the open cloud and continues across space in straight quiet lines. As the story unfolds further outward, attention shifts from this hidden core toward the turbulent outer atmosphere that bridges between the nuclear engine and the space around it. Far above the restless core of Alnilam lies a thin frontier where deep energy finally turns into visible light. This boundary region, called the photosphere, acts as the star's glowing skin and decides how the interior power appears to the Orion cloud. The photosphere is not a solid surface. It is a layer where gas becomes transparent enough for photons to escape more freely into space. Below it, light is trapped and scattered at almost every step. Above it, most photons travel long distances without meeting another particle. In this narrow zone, energy changes from being part of an internal flow to being part of the clear radiation that fills the cavity around the star. At this depth, the gas has a temperature of about 25,000 degrees. That figure feels more concrete when compared with a calmer point of reference. The surface sits at roughly 4 times the temperature of a typical yellow star like the Sun. This extra heat pushes the peak of the light towards shorter wavelengths and gives Alnilam its fierce blue-white tone. Yet the photosphere is more than just a hot blanket. It holds a delicate structure made from countless rising and sinking streams of gas. Imagine an ocean of glowing fluid spread around the star, its surface marked by bright patches and slightly dimmer lanes. Each patch traces regions where hotter gas has just risen from deeper layers. Each lane marks areas where cooler gas sinks back inward. The pattern forms a slow shimmering mosaic that never freezes into a fixed design. In place of waves and foam, there are cells and edges of light. The primary visible anchor here is that endless luminous ocean wrapped into a sphere with bright tiles sliding gently past one another. At small scales, individual tiles may span thousands of kilometers, but their outlines blur into one continuous field from any distance greater than a few stellar radii. When viewed across the Orion molecular cloud, the fine mosaic merges into a smooth disk whose brightness falls off slightly toward the edges. This gradient called limb darkening appears because light near the center comes from deeper, hotter layers, while light near the rim comes from shallower, cooler gas. In that way, a simple shading across the star's face carries a quiet record of its layered atmosphere. Moving farther outward, the disk shrinks into a single point that still encodes this information in the mix of colors and intensities. The photosphere also carries a kind of barcode in its spectrum. Spectral lines are narrow color bands that appear dimmer than the nearby continuum because certain atoms absorb specific energies. A simple definition holds them steady. A spectral line is a fingerprint of an element in a star. In the hot gas around Alnilam, hydrogen and helium dominate, joined by smaller amounts of heavier elements. Each type of atom prefers certain energy jumps. When photons with those energies cross the photosphere, some are absorbed by atoms in the gas. Later photons of similar energy may be released in new directions, so that fewer escape straight outward. The removed light leaves behind a thin, dark notch in the spectrum. The spectral pattern behaves like a set of labels on the physical conditions in the atmosphere. Broader lines signal higher pressure or faster motions. Stronger lines mark larger amounts of a given element. By reading these imprints in the light that leaves the photosphere, one can infer temperature, density, and composition, even though the gas itself is forever out of reach. This is where a clear limit of observation appears. The photosphere of Alnilam cannot be resolved into detailed cells and waves by direct imaging at current precision. The star presents itself as a bright point. Only its combined light reaches distant detectors. From that single integrated beam, all structure must be reconstructed. The resolution limit of those measurements prevents any view of individual bright patches or sinking lanes on the surface. Instead, models of radiative transfer and gas motion must fill in the gaps tuned by the observed spectrum and overall brightness. The outcome is not a photograph of the true surface, but a consistent physical picture that matches what the light allows. Even within this limit, the photosphere's role in the larger scene becomes clear. It is the layer where the star hands its energy to the surrounding cloud in a form that can travel almost unhindered for light years. Each photon that leaves this glowing skin carries a small part of the interior story. As it moves outward through the Orion molecular cloud, dust grains may scatter or absorb it, but its basic energy scale and color distribution were set in the photospheric layers. On small scales, the structure looks like an ocean of light filled with moving tiles and delicate gradients. On larger scales, the star shrinks to a simple bright bead in the belt. On still larger galactic scales, the photosphere becomes a thin, invisible shell around one of many massive stars tracing a spiral arm. In each frame, that narrow boundary still marks the transition between hidden nuclear processes and the calm glow that paints the surrounding gas. As the journey continues outward from this luminous skin, attention shifts from the surface patterns of light to the stream of radiation that leaves the star and begins to sculpt the nearby Orion material in more obvious geometric forms. At a modest distance from Alnilam, light leaving the photosphere enters a thicker band of dust and gas that begins to reshape its colour. In this region, the star's sharp blue-white radiance turns into a softer field, where hints of green emerge in the surrounding haze. What looks like a single note from one bright source becomes a quiet chord spread through the Orion molecular cloud. The change starts at the level of individual dust grains. Each grain is a tiny solid particle suspended in the gas. Many grains are made of silicates or carbon-rich material or icy coatings. Typical grains measure less than a micrometer across. That is smaller than fine volcanic ash drifting in a high plume. At this scale, light does not simply pass or stop, it bends or scatters or is absorbed and re-emitted depending on wavelength and grain size. Shorter wavelength light carries the star's strong blue component and emits these grains, then is redirected more often than longer wavelengths. Light behaves as if it were striking countless small beads bouncing sideways, so that some energy leaves the direct path and spreads into a surrounding glow. Along a direct line away from the star, this process makes the source look slightly dimmer and redder than it would in empty space. Off to the sides, scattered rays build a faint-coloured envelope that gently washes nearby parts of the cloud. The primary visual anchor here is a layered shell of mist around a central beacon. Inner regions glow in sharp tones, while outer sheets show mild teal and pale cyan tints. On small scales, that shell contains knots and streaks where the density of dust changes. Denser knots catch more light and shine as soft patches. Thinner regions barely glow at all and expose darker background lanes. The shell is not smooth, but still keeps a clear inner edge where direct starlight dominates and a broader outer band where reprocessed light takes over. Across that edge, a gradient in colour and brightness appears, marking the distance from pure stellar output to a mixture shaped by the cloud. A second process unfolds alongside scattering. Dust grains absorb some of the incoming energy and warm up by a small amount. Warm dust then re-emits that energy at longer wavelengths, often in the infrared. A simple definition holds this idea. Thermal emission is light released by matter because it is warm. In the case of Alnilam, this emission adds a low-energy background. It does not shine in vivid colours, but still fills the cavity with a soft, hidden glow. The brighter cyan and green hints come mainly from scattered shorter wavelength light, not from this deeper warmth. Even so, the two fields overlap and thicken the overall radiance. A helpful scale shift links the grain level to the size of the Orion complex. At the level of a single grain, interactions happen in fractions of a second as photons strike and depart. At the scale of the cloud, the gradual thinning or thickening of dust takes millions of years as gas flows and star formation reshape the region. The gentle green-tinged nucleus seen around Alnilam is therefore a momentary cross-section through processes that range from instantaneous scattering to slow structural drift. At any given time, only a fraction of the dust participates strongly in scattering. Other grains remain in cooler pockets until flows bring them into brighter lanes. Over future ages, the same light will pass through different arrangements of dust as filaments drift and disperse. Some filaments collapse and the shape of the coloured shell slowly changes. There is a clear limit to direct observation in this scene. No technique can track individual photons as they bounce from grain to grain, and no image can fully resolve every clump within the shell at once. Observations instead record averaged brightness across small patches of sky and at selected wavelength bands. Different wavelengths probe slightly different depths in the shell. Shorter wavelengths trace outer cleaner paths, while longer wavelengths sample more embedded layers. From these averages, models of scattering and absorption reconstruct likely grain sizes and densities. They map where most of the blue light is removed from the direct beam and where it reappears as a halo. The limit lies in angular resolution and in the simplifications needed to keep the models tractable. The true distribution of grains is more tangled than any current map can show. Even with this uncertainty, some features remain robust. The region close to Alnilam maintains a bright, slightly blue-dominated core. Surrounding that core, a ring-like zone inside the Orion cloud glows with blended light. In that zone, scattered blue and underlying red emission mix into delicate blue-green tones. Farther out, the scattered component fades and the cloud returns to a darker state. In mental imagery, the whole structure resembles a valley filled with layered fog at dusk. Near the centre of the valley, a clear pool reflects the fading sky in bright colours. Around it, bands of mist in different thicknesses shift the hues into softer tints that melt into the surrounding dim landscape. Replace the pool with the star and the mist with dust and gas, and the analogy follows the physics closely. Alnilam stands as the luminous basin at the centre of its own valley of haze. The photons that leave its photosphere pass through near shells and intermediate shells and distant filaments before they exit the Orion region. Each layer adds or removes a slight piece of colour information. Together they produce the impression of a green-edge blue nucleus set within a broader band of subdued light. As later sections move farther outward, the focus will widen from this local shell to more distant parts of the molecular cloud. The same radiation fields quietly help set the stage for future generations of stars. Around Alnilam, the push of light and particles steadily rearranges the nearest gas. This quiet sculpting turns a loose, uneven cloud into a hollowed shell with curved, glowing fronts. The process rests on two linked flows leaving the star at all times. One is radiation pressure, the gentle but constant push from photons. The other is the stellar wind, a faster stream of charged particles that carries mass as well as momentum. Together, they peel material away from the star's surroundings and stack it into new shapes along the edges of the cavity. At small distances from the photosphere, radiation pressure acts first. Photons leaving the hot surface strike dust grains and transfer tiny amounts of momentum. Each hit is small, but the number of hits is immense. Over long intervals, the sum of these gentle taps nudges grains outward. Gas tied to the grains through collisions and electric forces follows. Radiation pressure is the push of light on matter. It transforms steady brightness into a mild outward shove that never switches off. A single rounded number helps fix the strength of this effect. In 1 second, the star releases enough energy to match the lifetime output of a modest star like the Sun. That comparison is broad yet useful. It shows why even a slight push from each photon can accumulate into a large influence on nearby material. As grains drift outward under this steady push, the stellar wind streams past them. The wind is a flow of ions leaving the outer atmosphere at high speed. An object placed near the star would meet particles moving at thousands of kilometers per second. A simple comparison is a gale that never stops far faster than any wind in an atmosphere. Where the wind meets gas in the Orion cloud, it sweeps up the lighter material ahead of it and piles it into ridges. The key visual anchor is a broad, faintly glowing bubble with a rippled inner wall facing the star. Along that inner wall, gas is compressed and heated, while the region inside remains cleaner and less dense. On small scales, the wall holds dents and curves where it wraps around denser clumps that resist motion. Those clumps cast tapered shadows of lower pressure behind them. In those sheltered zones, gas stays cooler and somewhat thicker for a time. The pattern recalls sand dunes forming along a fence line. Wind carries grains across a field and drops them wherever the fence slows the flow. In the same way the stellar wind builds drifts of compressed gas and dust against the invisible fence formed by gravity and cloud density. The analogy does not capture every detail, but preserves the key idea of gathering material along a boundary. A gentle scale shift helps link the immediate surroundings of the star to the wider Orion region. Close in within a span of a few light days, the wind and radiation pressure carve a nearly spherical bubble. In that zone, conditions change significantly over times as short as years or centuries. Structures in the wind can travel across the cavity in those intervals. Farther out, over several light years, the same forces only slowly reshape the original molecular cloud. The shell thickens or thins over hundreds of thousands of years. Its inner surface creeps outward by small fractions of its radius over such long durations. At the scale of the wider Orion complex, the bubble around Alnilam becomes just one of many cavities, its influence woven into a patchwork of older and younger clearings. Inside, the shell gas density is lower and temperatures are higher than in the original cloud. Outside, the cold molecular material still dominates. The shell itself marks the transition. It forms a band where gas is partially ionized, partly neutral, and significantly compressed. Ionization is the removal of electrons from atoms by energetic photons. Here, photons from Alnilam strip electrons from hydrogen and other elements near the inner face of the shell. The result is a glowing layer where recombination and cooling processes release light of particular colors. That layer helps define the inner wall and adds to the subtle blue-green tones in the surrounding haze. There is an important limit to direct observation of these flows. The stellar wind itself is mostly invisible when viewed against the bright star. Its particles do not emit strong light on their own. Only where the wind collides with gas in the shell or beyond does it produce detectable signatures. The details of the flow must be inferred from line broadening and spectra from the shapes of emission regions and from models that combine radiation pressure with gas dynamics. The limit arises from current spatial resolution and from the lack of direct tracers close to the star. No image can show each ripple or eddy in the wind near the photosphere. Instead, the broad outline of the bubble and its approximate density contrast with the ambient cloud become the main clues. Even with these limits, the overall geometry remains clear. A roughly spherical or slightly elongated cavity surrounds Alnilam. Its inner wall faces the star and glows where ionized gas cools. Its outer side presses against colder molecular gas and may trigger new compressions and seeds of collapse. Inside the cavity, the gas is thinner and more transparent. Outward streaming light crosses this cleaned region with fewer encounters before it meets the shell. From there, some photons escape into the greater molecular cloud and some scatter sideways along the inner surface. In a wider frame along the belt, the cavity sits between neighbouring dense filaments and darker lanes. The bubble stretches over a region comparable to the 10 or 20 light-years that separate many star-forming knots in Orion. Over its lifetime, it will gradually grow and perhaps merge with nearby cavities driven by other massive stars. In this way, Alnilam's steady wind and radiation do more than light up the cloud. They also rearrange the cold material into arcs, ridges, and cleared pockets that prepare the structure for later chapters of star formation. As the perspective moves farther into those filaments, attention turns from the immediate bubble to the denser strands that still survive in the star's wider neighbourhood. Beyond the bright bubble around Alnilam, the Orion molecular cloud gathers itself into long dark filaments that still resist the star's clearing power. These filaments act as sheltered channels where gravity and radiation meet, shaping the next steps of structure in the region. Each strand is a cold river of gas and dust winding through a warmer, thinner medium. Within them, conditions remain dense enough for new clumps and eventual star-forming cores to emerge. At small scales, a filament is a narrow cylinder of higher density material with a clear physical edge. Inside, gas stays cool and slowly flows along the strand. Outside, temperature is higher and density falls away. The boundary can be pictured as a soft, rounded ridge, not a hard wall. Where light from Alnilam brushes this ridge, it outlines the filament with a faint glow, while the interior remains dark. The main visual anchor is a network of shadowed ribbons threaded through a pale blue-green haze, each ribbon traced by a thin luminous rim on its sunward side. In that scene, the star's radiation does not erase the filaments. It highlights them and changes their internal balance. One rounded number helps set the scale of these channels. A typical filament near Alnilam can stretch for about 10 light years from end to end. That length is comparable to the distance a signal would cover by crossing several times the gap between neighbouring low-mass stars. Across such a span, the strand narrows to a width much smaller than its length, like a cord laid across a vast floor. Along this cord, density rises and falls. Slight over-densities act as seeds where gravity gains a small advantage over pressure and turbulence. Radiation from Alnilam reaches the outer layers of the filaments and compresses them further. This process is sometimes called radiation-driven compression. It is the strengthening of density in a cloud region under the steady push of external light. In the Orion setting, the effect remains gentle but persistent. On the star-facing side of a filament, gas layers feel a small extra pressure where photons are absorbed and scattered. Over long times, this extra push can nudge material inward, thickening the strand and sharpening its profile. On the far side, shadowed gas relaxes in a calmer field. The difference across the filament sets up internal motions that slowly rearrange matter. A helpful analogy is a long curtain hanging in a weak breeze inside a quiet room. Where the breeze meets the fabric, it presses folds together and makes some regions thicker, while other sections billow gently. The curtain does not tear or vanish. It redistributes its creases and gathers in some places. Replace the breeze with radiation from Alnilam, and the curtain with a dense filament, and the mental picture follows the physics closely. Within the thickest folds of these cosmic curtains, small pockets reach the conditions needed for gravitational collapse. Collapse is the inward fall of material under its own gravity when no other support can hold it up. Inside a contracting pocket, density climbs and temperature slowly rises. Over hundreds of thousands of years, the pocket can shrink from a cloud-wide scale to a concentrated core. At every stage, gas and dust remain wrapped inside opaque layers. In this regime, gravity, thermal pressure, and the external radiation field all contribute to the final shape and mass of the forming core. A gentle scale shift links the fate of one core to the broader Orion pattern. On the smallest scales, collapse affects regions that might span only fractions of a light year. On intermediate scales, filaments several light years long supply material to several such cores at once, feeding them along the ribbon. On the largest scales, across tens of light years, a whole web of filaments connected to Alnilam's neighbourhood sets the budget of gas available for future generations of stars. There is an important limit to intuition and to direct observation here. The interiors of these filaments are cold and often invisible in ordinary light. Dust blocks most background radiation. Only selected wavelengths from specific molecules leak information from within. Measurements rely on spectral lines from molecular gas and on the faint glow of dust at longer wavelengths. These data offer average velocities, densities, and temperatures along each line of sight. They cannot show every twist or knot separately. Limited angular resolution and the overlapping of different strands along the same viewing path further blur the picture. The geometry that emerges is therefore a combination of direct mapping and modelled structure, not a perfect photograph of each filament's true three-dimensional shape. Even with those limits, some features remain well anchored. Filaments near Alnilam tend to bend slightly around the bubble carved by its wind and radiation. Their bright rims face the star and mark where the outer layers are compressed or ionized. Their darker interiors trace where shielded gas remains ready for slow collapse. In some places, chains of dense clumps line up along a single strand like beads on a string. Each bead signals a region where internal support has weakened and where star-forming cores may already be forming or will form in the future. On larger scales across Orion, these star-bearing filaments interlock with others or shaped by different massive stars. The network resembles the grain in a piece of wood running in preferred directions, yet carrying knots and swirls. Alnilam influences only part of this grain, but does so in a sustained way, turning nearby filaments into shaped channels rather than random fragments. In this way, the star's presence guides where new clusters may one day gather. As the story moves further along these filaments, the focus will shift from large-scale channels of gas to the smaller, denser knots within them, where the first quiet signs of future stellar cores begin to appear. Deep inside the darker filaments near Alnilam, patches of gas quietly thicken into rounded knots. These knots are dense cores, the earliest seeds of later stars. Each core is colder than its surroundings and more strongly bound by gravity. It gathers mass from the filament and slowly separates its fate from the rest of the cloud. In a simple mental picture, the filament becomes a long, dim strip with small, heavier droplets spaced along its length. The main visual anchor here is a cluster of soft, nearly spherical blobs, glowing faintly inside a muted blue-green background, each blob edged by a slightly brighter rim. Within a single core, density rises toward the center, while temperature stays low. Gas moves at only a few hundred meters per second, far slower than any speed associated with Alnilam's wind. Pressure cannot fully balance gravity here. Over time, inward pull slowly wins. A single rounded figure helps hold the scale of these seeds. A typical core may contain a few times the mass of the Sun. That mass sits packed into a region only a fraction of a light year across, like a modest stone pressed deep inside a much larger cushion. The cushion is the parent filament supplying fresh material through slow inflow. Core formation rests on a simple threshold idea. When a region becomes dense and cold enough, gravity overcomes internal motions and external support. That threshold depends on temperature, density, and size. Once crossed, collapse becomes easier than expansion. Collapsing gas does not fall straight in along every direction. Instead, material streams inward through preferred channels set by local magnetic fields and by the shape of the filament. Some flow lines bend and twist, wrapping around the core like threads of smoke curling into a central knot. At close range, the boundary between core and envelope appears as a gradual change, not a sharp surface. Outside the core, L follows the general filament pattern. Inside, motions turn more inward focused and more ordered. A gentle scale shift connects these small knots to larger regions. On the scale of tenths of a light year, a core is the main structure with an unmistakable inward gradient. On the scale of several light years, a string of such cores appears as a chain inside one filament. On the scale of 10 or 20 light years around Alnilam, many such filaments crisscross the cleared cavity edge, each holding its own family of dense pockets. In this way, future stars gather inside the same cloud that now frames the bright belt star. Radiation from Alnilam does not simply crush or evaporate these forming cores. It shapes their outer layers in more subtle ways. On the side facing the star, the envelope experiences heating and gentle compression. Some of this heated gas flows away and is lost. Deeper inside, where dust shades the radiation, the core stays cold enough to continue contracting. The result is a layered structure with a slightly warmer skin and a cooler interior. The concept of shielding becomes important here. Shielding is the blocking of energetic photons by intervening matter. Dust and gas in the outer core layers absorb and scatter much of the radiation that would otherwise reach the center. That shielding lets the inner regions hug their low temperatures and high densities. The outer shell and inner core thus play different roles as the structure evolves. A useful analogy is a drop of thicker ink forming within a pale watercolor wash. From far away, the whole region looks like a single soft patch of color. Closer in, a concentrated stain stands out inside the lighter surrounding layer. The outer wash mirrors the filament faint and extended. The ink drop matches the dense core deeper and more compact. In the Orion cloud, the analogy follows the behavior of density and temperature rather than pigment. There is a strong limit to direct observation of these cores. Their interiors are cold and heavily obscured by dust. Ordinary visible light does not escape in a clean way. The central regions are effectively invisible in that band. Observations rely instead on longer wavelength radiation and on spectral lines from specific molecules that trace dense gas. These lines reveal average motions along the line of sight and estimate densities and temperatures. However, they do not give a clear picture of small-scale flows inside the thickest parts. The limit comes from both resolution and optical depth. Telescopes cannot yet isolate every internal swirl or tiny fragment. Models must therefore combine the measured line profiles with basic gravitational physics to infer the likely internal structure and collapse rate. Even with these limits, some secure patterns emerge. Cores closer to Alnilam tend to show more sculpted outer edges, where radiation has compressed or eroded their skins. Cores deeper inside, shaded parts of the filaments look more symmetric and less disturbed. The distribution of core masses also follows the density pattern of the filaments. Heavier filaments feed more massive cores, while thinner strands support only smaller seeds. Over time, some cores will grow and cross a second threshold, beginning true protostellar collapse. Others may disperse if external pressures change, or if turbulence stirs them apart. On longer timescales of hundreds of thousands to millions of years, the set of cores near Alnilam will either transform into a cluster of young stars or fade into the background cloud. In a wider view, this process repeats across the Orion complex, linking the life of the belt star to a larger cycle. Massive objects like Alnilam help carve cavities and shape filaments. Those filaments then condense into cores that may later form new stars, some massive, many small. The present scene around Alnilam is therefore a snapshot of several stages layered together. A mature, bright star illuminates the cloud, while nearby seeds of future stars rest half-hidden in dense knots. As later sections move forward in time, attention will turn toward how Alnilam itself evolves away from its stable main phase, and how its eventual changes feed fresh material back into the same cloud that now shelters these quiet cores. At this stage in its life, Alnilam looks steady and unchanging against the soft band of the Orion cloud. In reality, the star stands in the middle of a rapid life cycle, racing through its fuel far faster than quieter neighbours. Its current blue-white phase is only one chapter in a story that runs from compact birth to swollen giant, and finally to violent end. Inside, the core hydrogen fusion still supplies most of the energy. Each reaction converts a tiny fraction of the mass into light and heat. The rate of these reactions depends strongly on temperature. Because Alnilam is massive and its core is very hot, fusion runs far more quickly than in a smaller, cooler star. A calm yellow star might shine for around 10 billion years. A star like Alnilam may pass through its bright life in only about 5 million years. It is as if one lamp sips fuel through a thin wick over a long winter. Another burns its oil through a wide, bright flame in a single evening. The same store of fuel produces far more light per moment but lasts for a much shorter span. That quick pace changes the structure inside the star. As hydrogen steadily turns into helium in the core, the mix of elements changes the balance between pressure and gravity. Helium is heavier and contributes less to keeping the gas buoyant. Over time, the central region contracts slightly and heats even more. The hotter core then speeds up fusion, which in turn releases more energy. This feedback pushes the surrounding layers outward. At the same time, fusion begins to move from the very center to a shell around a growing helium core. Shell burning is fusion that occurs in a thin layer wrapped around an inert inner region. It acts like an extra furnace added above an old one. In Alnilam, shell burning will cause the outer layers to swell and cool. This change will slowly alter the star's color and size. From a distance, the shift will turn a compact blue point into a larger, somewhat redder star. In a cross-section, the internal structure begins to resemble a tower of stacked hourglasses. Each level represents a different fusion shell that empties at its own rate. The tower glows brightest near the core, where the finest sand still falls fastest. As the star continues through this layered burning, it also loses material from its surface. Strong radiation and stellar winds peel away outer layers and carry them into surrounding space. Over a few 100,000 years, Alnilam can shed several solar masses of gas. That amount of matter is comparable to emptying a small star into the Orion cloud. The lost material does not vanish. It spreads into the existing cavity as a slow enriched breeze. Close to the star, this breeze adds to the density of the inner bubble and thickens the shell where wind meets the original cloud. Farther out, it blends with wider flows and gradually becomes part of the shared reservoir that feeds future cores. A gentle scale shift connects these internal changes to the larger environment. In the core, reaction times are measured in fractions of seconds as nuclei collide. In the shells, energy takes thousands of years to work its way outward. At the level of the whole star, major structural changes unfold over hundreds of thousands of years. At the level of the Orion complex, the effects of mass loss and radiation shaping play out over millions of years. Beyond that, the galaxy's spiral arm holds sequences of such massive stars. Their lives alter the chemical mix of gas over tens or hundreds of millions of years. There is a strict limit to direct intuition here. The entire main life of Alnilam fits into a span that is short compared with the history of a galaxy. It is still far longer than any direct monitoring could ever cover in detail. No observation can watch the star evolve smoothly from hot blue phase through swelling and final collapse. Instead, knowledge comes from comparing many stars of different masses and ages. Models then stitch these snapshots into a continuous path. The past and future must be reconstructed through calculations that blend nuclear physics and gas dynamics and radiation transport. Even with these constraints, some outcomes remain secure. Alnilam will not drift gently into a quiet fading. Its large mass sets it on a path that leads beyond shell burning to stages where heavier elements form in its core. When those stages end, gravity will overpower all forms of pressure and drive a rapid collapse. The outer layers will then be expelled in a powerful explosion, leaving behind a compact remnant and a shell of enriched debris. In the Orion cloud, that shell will expand and mix with the pre-existing gas. On smaller scales, close to the former star, it will draw glowing arcs and knots into the sky. On larger scales, it will scatter heavy elements like oxygen and carbon and silicon into the shared medium. Those elements will later appear in the cold filaments and dense cores that follow. The present blue nucleus of the belt is therefore not just a light source, it is a temporary furnace that prepares material for later worlds. Over cosmic time, such cycles repeat again and again along the arm. Each repetition leaves the gas a little richer and the structures a little more intricate. As the script moves forward, attention will turn from this future sketch of Alnilam's fate to the wider belt and its place in the spiral arm. In that wider frame, many such lives overlap and combine to shape the long-term appearance of the Orion region. On still larger scales, Alnilam stops being a single bright centerpiece and becomes one node inside a wide web of clouds and hot stars. That web is the Orion complex, a star-forming region that stretches across hundreds of light-years along a spiral arm. Within this space, dark molecular lanes glowing nebulae and scattered massive stars form a connected landscape rather than separate objects. In a face-on view, the complex resembles a broad river delta of light and shadow spread across a dark sea. Bright patches mark active channels where new stars are shaping the gas. Dark channels trace where cold material waits in reserve. The main visual anchor is this branching delta with Alnilam sitting near one of its luminous junctions, turning part of the flow into a clear bright pool. A rounded number holds the size of this environment. The Orion complex spans roughly 400 light-years from end to end. On a simple model, where the distance from the Sun to its nearest neighbour is reduced to 1 metre, the complex would fill a modest town. Within that town-sized volume, cold clouds weave between warmer cavities and groups of massive stars mark districts of more intense activity. Alnilam belongs to such a group, an association of hot young stars that share a common origin, the same broad reservoir of gas, these massive stars do not stay close together forever. Each follows its own orbit inside the galaxy. For a few million years, however, they cluster enough to carve overlapping bubbles and illuminate shared filaments. Their combined radiation shapes the Orion complex into an irregular but coherent structure. Some regions become bright arcs and shells, others turn into long rugged walls between cleared cavities. The Orion belt runs across one of these walls, with Alnitak, Alnilam and Mintaka tracing a line where dense material and blown-out zones meet. At small scales near each star, local cavities and shells dominate. At intermediate scales of tens of light years, these cavities merge into a patchwork of overlapping bubbles. At the scale of the full complex, that patchwork forms the bright parts of the river delta pattern embedded in wider lanes of dark molecular gas. The complex moves as a whole through the galactic disk carried along by the rotation of the spiral arm. While it moves, internal processes keep changing its layout. Some bubbles expand and join, some filaments thin or break. New dense cores appear, while older ones form stars and disperse. Over about 10 million years, the appearance of the Orion complex will drift from a pattern dominated by cold lanes to one containing more cavities and hot stars. Eventually, as gas turns into stars or is blown away, the complex will fade as a star-forming site. There is a clear limit to direct observation when looking at this wide structure. From within the galaxy, the Orion complex appears projected onto the sky as a two-dimensional pattern. Distances along the line of sight remain hidden. Observations must use velocities, colours and careful modelling to reconstruct depth. Spectral lines from the gas reveal motions toward or away from the observer. Changes in brightness at different wavelengths show where dust is thickest. Even so, overlapping clouds can mimic a single lane, and separate features can seem connected. The true three-dimensional shape must therefore be built from multiple kinds of data and remains partly uncertain. Resolution also limits what can be seen, and filaments blur together. Small groups of young stars hide inside opaque knots. Despite these limits, the broad connections remain secure. It is clear that Alnilam, the belt, and nearby nebulae share a common stage in one complex. Within this stage, gradients in radiation and density run smoothly from one region to the next. Around Alnilam, cavities and compressed shells show where its light and wind dominate. A short distance away, other hot stars carve their own zones and their edges meet and overlap. Between these zones, the coldest molecular gas lies in elongated ridges that tie the pattern together. A useful analogy for this shared structure is a patch of melting ice on a dark lake. Thick plates of ice stand in for the densest molecular clouds. Narrow leads of open water trace the cavities where gas has been cleared or heated. Thin wet slush along the edges matches the mixed, partially heated layers around bubbles. One plate of ice can hold several thin cracks and openings, just as one molecular cloud can hold several cavities from different massive stars. In this picture, Alnilam is one broad opening in the ice sheet where light reflects strongly from the exposed water. The analogy preserves the idea of connected regions in different phases, rather than isolated objects. Within the larger galactic context, the Orion complex is itself only one patch on a much longer spiral arm. The arm curves around the galaxy over tens of thousands of light years. Along this curve, other complexes share similar roles. Each one is a place where cold gas gathers, forms massive stars, and then changes shape under their influence. As time passes, the arm will carry these complexes through different galactic environments. Some may encounter gentle tidal effects. Others may meet older cavities from past generations of massive stars. In this slow drift, the Orion complex and its bright belt form a temporary pattern no more permanent than a swirl in a wide river. For now, the structure remains recognizable. A trio of aligned stars outlines the belt. Below and around them, glowing nebulae trace arcs and loops. Dark lanes cut through the light like long, quiet channels. Within one of those bright nodes, Alnilam holds its place as a green-edged blue core, marking the centre of a local clearing. As the narrative widens in the next section, focus will shift from this single complex to the longer timescales and chemical changes that link Alnilam and Orion to past and future generations of stars in the galactic disk. Across the Orion complex, the gas surrounding Alnilam carries more than light and motion. It carries a slow record of changing chemistry. That record links the bright belt star to older generations of massive stars that once lived and died along the same spiral arm. Long before Alnilam ignites, earlier stars fuse light elements into heavier ones and then return part of that processed material to the cloud through winds and explosions. In this way, the Orion region becomes a mixture of pristine hydrogen and helium, and a modest share of heavier elements all stirred together over long stretches of time. A simple term helps hold this idea. Chemical enrichment is the build-up of heavier elements and gas over many stellar lives. Near Alnilam, enrichment appears in the dust grains and molecules that fill the filaments and dense cores. Oxygen, carbon, silicon, and iron atoms sit inside tiny solids or drift in cold gas. These elements once formed deep in older stellar cores or in their outer layers during giant phases. When those stars ended their lives, they expelled fragments into the interstellar medium. Over millions of years, turbulent motions and large-scale flows mix those fragments into broader clouds. The main visual anchor here is a stack of faintly coloured translucent layers inside a polished gemstone, each layer representing material from a different generation of stars. No true edges separate them, yet slight shifts in tint hint at different histories. In the Orion cloud, the layers are made of gas shells and dust populations with slightly different compositions stacked and blended. A single rounded number helps set the timescale. The Milky Way has been forming stars for around 10 billion years. Compared with that age, Alnilam's life of a few million years is a brief flash. It resembles one short spark inside a long-running forge. Earlier sparks have already added metals to the gas. Later sparks will do the same. Each event moves the average composition in small steps. Inside the dust grains near Alnilam, this history shows up as thin coats and mixed structures. Some grains contain silicate cores formed in old outflows. Others carry carbon-rich mantles grown in later cycles. As these grains drift through the star's radiation field, they heat, cool, and sometimes fragment, but they keep the heavy elements bound in solid form. Gas around them holds related atoms and simple molecules. On scales of light days to light months near the star, radiation pressure and shocks rearrange these grains. On scales of tens to hundreds of light years across Orion, large flows driven by many massive stars redistribute enriched gas between complexes. Over even larger scales around the galaxy, spiral arm patterns and differential rotation slowly smear these contributions into a broader gradient. At this point, intuition reaches a limit. It is impossible to follow a single atom from its birth in one stellar core through every collision and drift until it rests in a dust grain near Alnilam. Observations cannot tag individual atoms with serial numbers. Instead, they measure average abundances in gas and stars in different regions. Spectral lines reveal how much of each element is present along a line of sight. Models then connect these measurements with histories of star formation, mass loss, and mixing. The limit lies in the resolution of the data and in the approximations of the models. Small pockets of unusually enriched or unusually pristine gas can hide below the averaging scale. Even so, the big pattern remains well grounded. Regions like Orion show higher heavy element content than very old remote clouds. That difference implies that several waves of massive stars have already lived and died there. In Alnilam's neighbourhood, this enriched material plays quiet roles in many structures already described. It changes how efficiently gas cools inside filaments and cores. Efficient cooling allows regions to reach lower temperatures and higher densities, helping collapse proceed. It affects the opacity of dust grains and therefore the way light from the belt star is scattered or absorbed. Fine differences in composition decide which wavelengths are blocked more strongly and which pass more freely. In that way, old stellar generations influence the exact green-blue shades seen in the haze around Alnilam. A useful scale shift ties the microscopic and the grand together. On the smallest scale, a single iron atom inside a grain might influence how the grain absorbs certain colours. On the scale of a dense core, the combined effect of many such grains, its cooling rates and affects the mass distribution of forming stars. On the scale of the Orion complex, the average heavy element content shapes the overall efficiency with which gas converts into stars over tens of millions of years. On the galactic scale, similar processes in many complexes slowly move the entire disk from metal poor to metal-richer states. Within this layered context, Alnilam's own future explosion becomes another step in the sequence. During its late burning stages, the core will assemble heavier nuclei up to iron and beyond. When collapse and explosion finally occur, a large fraction of those products will spray into space as a hot expanding cloud. That new cloud will cross paths with older layers, ploughing through pre-existing gas and dust and mixing freshly formed elements with those that have cycled many times. Over time, the mixture will cool and fragment, feeding new filaments and cores. Some of those future cores may one day host planets with solid surfaces, built largely from elements released in events like Alnilam's death. Although those possibilities lie far in the future, the quiet preconditions already exist in the current Orion material. The present scene around the belt star can therefore be seen as one frame in a long movie of composition, where each bright, massive star briefly reworks the chemical script. For now, the layers in the Orion gemstone remain only gently disturbed by Alnilam's light and wind. As the narrative moves onward, attention will turn from this chemical layering to the more subtle ways in which distance and time change the apparent face of the belt, altering how its alignment and brightness will look to observers in other eras and other corners of the galaxy. At large distances from the Orion region, the belt that holds Alnilam seems like a fixed decoration pinned against the dark. In truth, its alignment and apparent brightness slowly drift as stars move and gas disperses. Vantage points also change along the spiral arm. The pattern that now frames Alnilam as a central bead in a straight line is a temporary arrangement in a moving system. Each belt star follows its own orbit around the galactic centre, guided by gravity from the disk and the combined pull of nearby mass. The orbits trace long, slightly curved paths that differ in speed and direction. Over time, these differences accumulate. The once straight line gradually bends into new shapes and slowly stretches and tilts. On small timescales of years or centuries, the change is too slight to see without careful analysis of positions. On larger spans of millions of years, the projected geometry of the belt changes enough that the familiar three-star line becomes a more uneven figure. A single rounded number helps anchor these motions. Over about 100 million years, a typical star in the disk can complete a full orbit around the galactic centre. This journey is similar to a slowly turning ring in a vast clock where each marker moves at its own pace around the dial. The Orion complex and its belt ride along this ring, carrying Alnilam and its neighbours through regions with slightly different mass distributions and tidal pulls. Close in at distances of a few light years, the geometry of gas shells and filaments still dominates the view. At intermediate distances of tens to hundreds of light years, the belt appears as a small straight segment embedded in the Orion pattern. Farther out across thousands of light years, the same three stars shrink into a faint trace with a gentle curve within a spiral arm. The main visual anchor is a layered perspective like a stack of transparent sheets. Each sheet shows the belt at a different zoom level with a subtle rotation and shift. The apparent brightness of Alnilam also evolves with both intrinsic change and changing surroundings. As it ages, its luminosity rises and falls according to inner fusion stages and mass loss. In some phases, the star may grow larger and cooler and spread its light over a broader surface with a different colour balance. In others, short-lived bursts of mass loss can thicken local dust and produce temporary dimming as grains absorb and re-emit more radiation. At the same time, dust and gas in the Orion cloud drift and slowly thin or clump along the line of sight. These flows alter how much light is scattered or blocked. In one era, Alnilam may shine through a relatively clear channel and show its full blue-white strength. In another stage, slow shifts in dust lanes can place thicker filaments between the star and distant vantage points. Those changes soften its colour and reduce its intensity. Over long periods, the combination of intrinsic and environmental changes means the belt does not keep a fixed balance of brightness among its three main stars. There is a firm limit to direct perception of these slow changes from any single world bound to one star. Lifetimes of stable conditions span only tiny fractions of the pattern's evolution. No continuous record can follow every subtle bend of the line or every gentle rise and fall in brightness. Instead, knowledge of motion and change comes from comparisons among many snapshots. Positions of stars are recorded at intervals, then differences reveal proper motions and drifts. Brightness levels are tracked over time and compared with models of stellar evolution and dust behaviour. The limit lies in both duration and precision. Finite observing spans capture only a small arc of the full galactic orbit, and measurement uncertainties leave small motions hidden below the noise level. Even with those limits, the general trend is clear. The present belt is a passing configuration one frame in a long sequence. For long stretches, it maintains a near straight alignment with Alnilam, occupying the central position. For other stretches, the stars will appear slightly more spread and may form a shallower or steeper line as their projected positions shift. Seen from other regions of the galaxy, the viewing angle to the Orion arm can differ. In those cases, the pattern may never match the appearance it has from the current location. A useful analogy ties these ideas together. Imagine a set of three small lights attached to a slowly rotating flexible band. From one side the lights line up neatly, from another side they form an open triangle. As the band turns, the distances and angles seen in projection keep changing. The physical spacing of the lights changes only slowly. In the galaxy orbits and local gravitational tugs combine with gentle flexing of the spiral arm to play the role of the band's motion. The apparent pattern across the sky reflects this quiet dance rather than any rigid structure. Within the Orion region, the changing alignment and brightness of the belt also feed back into how gas responds. Slight rebalancing of radiation flows can shift which filaments receive the most intense illumination and which shells glow most strongly. Over millions of years, bright edges may migrate along the cloud as the projected line of the belt tilts and stars drift past dense lanes. Eventually, Alnilam leaves its current phase and approaches later stages. Its contribution to the belt's central glow will then change more radically. The blue-white nucleus of the line will soften and slowly swell. Later it will vanish into an expanding shell of debris. Future stars born from that debris may one day occupy new positions within the same general region. They could trace a different alignment across a slightly altered cloud. As the narrative begins to slow, attention turns from these evolving patterns back toward the present view. In that view, the green edge blue core settles once more into focus as a calm guide point within the gradually changing Orion sky. Far beyond the Orion region, Alnilam's story blends into a wider pattern of making and remaking structure in the galactic disk. This pattern behaves like a slow-breathing cycle for gas and stars. Dense clouds gather, form bright, massive objects, and then dissolve back into more diffuse material. Around Alnilam, the current breath sits near its peak. A rich cloud has already produced the belt and nearby clusters, yet large reservoirs of cold gas still wait in surrounding lanes. On small scales, the effects of this cycle appear as reshaped shells, carved filaments, and dense cores described earlier. On larger scales, they appear as waves of star formation that drift along the spiral arm. Each wave leaves behind clusters and cavities while preparing conditions for the next. A useful term here is feedback. Feedback is the return of energy and matter from stars into the gas that once fed them. In the Orion complex, feedback takes many forms. Alnilam provides intense radiation-strong winds, and later in its life a final explosion. Lower mass stars nearby add gentler outflows and ultraviolet light. Together they heat, compress and stir the surrounding gas. Some regions become too warm and diffuse to form new stars. Others become denser and cooler in sheltered pockets, making collapse easier. The main visual anchor for this grand cycle is a layered coral reef in a clear sea. Old skeletons form the inner structure. Living coral adds fresh branches on the surface. Small gaps shelter new growth, while waves and currents sculpt the outer edges. In the galaxy, old stellar generations correspond to the reef's foundation. Current clouds, bright stars, and young clusters form the active coral layer. Cavities and filaments provide the sheltered gaps where new structures begin. A single rounded figure holds the pace of this slow breathing. Across the Milky Way, gas turns into stars at roughly 1 or 2 solar masses each year. That rate is similar to sprinkling a thin layer of sand over a wide beach every year. Each individual grain seems negligible. Over millions of years, the accumulation becomes a deep bed. In the same way, steady conversion of gas and steady feedback from massive stars gradually change how much cold material remains in any given arm segment. Near Alnilam, this process means that the dense lanes feeding the Orion complex will not last forever. On scales of tens of millions of years, star formation winds and explosions will thin those lanes. Some gas will be locked into long-lived low-mass stars. Some will be ionized and pushed into the halo in fountains of warm material. Some will cool again and rain back toward the plane, ready to be gathered into new complexes. There is an important limit to direct observation of this breathing cycle. No single vantage point can track many full rounds of gathering, bursting into stars and dispersing. The time scales exceed any stable observing window. Instead, clues come from comparing different regions at different apparent spot years. Some complexes resemble Orion with active, massive stars and rich clouds. Others show mostly old cavities and fading clusters. Still others remain dark with dense gas but few detectable hot stars. Models then string these snapshots into a sequence. The limit lies in the ambiguity of those snapshots and in the resolution of the data. Projection effects and hidden gas can make a region appear younger or older than it is. Even with those uncertainties the general picture holds. In the long-term cycles like the one around Alnilam regulate how quickly the galaxy consumes its gas. If feedback were too strong, clouds would disperse quickly and star formation would stall. If feedback were too weak, gas would collapse too fast into clusters and leave little material for future generations. Around the belt, the balance appears moderate. Massive stars carve cavities and enrich the gas, yet broad filaments still survive and feed cold cores. A gentle scale shift connects this single complex to the entire disk. On the smallest scales, feedback from Alnilam alters densities and temperatures within a few light years. On intermediate scales of hundreds of light years combined, feedback from many hot stars shapes the Orion complex. On galactic scales of tens of thousands of light years, hundreds of such complexes collectively set the overall rate at which the disk brightens with new stars or dims as gas is locked away. Over billions of years, this regulation decides whether the galaxy remains a place with active spiral arms and glowing nebulae, or fades toward a quieter state. Within that large framework, the current scene remains finely detailed and calm. The bright green-edged blue of Alnilam lights up one side of a carved cavity. Filaments extend outward like deliberate strokes, some still building cores, others already thinning. Dense knots hold the quiet promise of later stars. Farther out, the spiral arm carries the entire pattern along its orbit, turning slowly in the dark halo. Other complexes rise and fade ahead and behind. The reef of stars and gas persists even as individual branches grow and crumble. As the narrative moves toward its closing sections, attention will draw more tightly back to the immediate light around Alnilam, letting the wider cycles recede into a gentle backdrop, while the local glow settles into a guide for rest. Seen against the background of cosmic history, Alnilam's bright core becomes one brief, precise accent inside a much longer composition. The universe has been forming structure for about 13 billion years, while this single star spends only a few million of those years in its present blue phase. In that contrast, the belt and the Orion cloud turn into one detailed pattern, stitched into a far wider canvas of galaxies, clusters, and the thin threads of the cosmic web. On the smallest scales already described sharp boundaries around Alnilam's cavity mark where hot gas meets cooler cloud shading from bright ionized edges into darker, denser interiors. On larger scales within the Milky Way, the Orion arm holds chains of such cavities that trace a gentle curve around the disk. Viewed from outside the galaxy, that curve would appear as one faint swept brushstroke within a wide rotating system, its light dim, compared with the central bulge and outer halo. The main visual anchor for this section is a long-arched hallway lined with quiet alcoves. Each alcove holds a small glowing sphere set into patterned stone. Some spheres shine blue, some red, some already dark. The Orion belt occupies one alcove with Alnilam as the central sphere and the gas around it forming carved reliefs on the walls. Other alcoves down the hallway hold other star-forming regions and ancient remnants. The hallway itself stands for the disk of the galaxy, and further for the chain of galaxies bound together in a larger structure. In this image, walking from one alcove to another would be like moving across millions of light years passing different epochs and environments. A gentle scale shift connects the phases of Alnilam's life to the layered ages of the universe. In the earliest era before galaxies exist, matter spreads almost evenly, with only small ripples in density. Later, those ripples grow into filaments and knots where gas falls together and builds the first galaxies. Within those galaxies, dense clouds gather and form massive stars like Alnilam. A star of this type lives and dies quickly, yet its beginning still depends on far older steps that built the galaxy and the arm. When Alnilam ends in an explosion, its debris will seed gas for later generations, which in turn serve as small influences on whatever future structures arise as the galaxy continues to evolve. In this way, a short-lived star sits nested inside a history that runs from the smooth early universe to a more clumped, structured present and beyond. There is a clear limit to intuition when trying to hold all these scales at once. Human senses evolved to track days, years, and simple distances, not billions of years and spans between galaxies. Direct observation also faces strict boundaries. Only a small portion of the universe is visible, and within that portion light carries information from finite ranges in time and space. At great distances, galaxies appear as tiny dim smudges, and details of individual stars vanish. Even within the Milky Way, dust lanes obscure many regions and restrict clear lines of sight. To bridge these gaps, models must combine what is seen in nearby regions like Orion with what is seen in distant systems at different redshifts. The limit lies in how finely data can resolve small structures and how securely their histories can be reconstructed from a few observable properties. Even with those constraints, broad relationships stay firm. Massive stars like Alnilam appear in many young galaxies and always influence their surroundings through light wind and heavy element production. Their brief lives help regulate star formation and enrich gas across cosmic time. Returning to the Orion alcove in the hallway, the carved reliefs around the central sphere carry fine detail that stems from these processes. Near the base, shallow grooves represent filaments guiding gas into dense knots. Above them, smooth raised arcs trace cavities blown by radiation and winds. At the top, faint branching lines indicate where future flows may carry enriched gas outward. The sphere itself glows with a gentle blue-green edge, marking the hot surface and the ionized shell around it. Farther down the hallway, some alcoves hold only dark, cracked stone representing regions where gas is long gone and only old stars remain. Others hold groups of smaller steady spheres, standing for mature clusters where massive stars have already ended. This contrast shows how the Orion Belt's current brightness fits into a larger sequence neither the first nor the last time such patterns appear. A further scale shift step still outward. Galaxies like the Milky Way cluster together in groups and filaments connected by gravity into the cosmic web. In those huge structures, individual star-forming regions merge into mere flecks. The detailed scene around Alnilam becomes one of countless similar knots scattered through the web. Yet even here, the same basic story repeats. Gas falls into potential wells-formed stars and is stirred and enriched by their feedback. Over time, more matter settles into long-lived stars and remnants, while the overall rate of new star formation slowly declines. The cosmic hallway extends, but new glowing spheres appear less frequently along its walls. Still in the current epoch, the Orion alcove remains active and bright. Within it, the green-edged blue core casts steady light into the cavity. Filaments curve like slow streams of smoke toward dense, quiet knots. At the boundary of the bubble, gradients of density and ionization form a soft, layered shell. Beyond that shell, the broader arm holds other clouds in various stages of collapse and dispersal, all carried together around the galactic center. As attention narrows again from the larger scales, the wide hallway and distant web recede to a faint suggestion. The focus returns to the single alcove, to the carved shell and the luminous sphere at its center. In that close frame, Alnilam's light becomes less a data point in a vast history, and more a steady calming presence in a slowly changing sky. The next and final section will rest within that nearness, letting the details of the cavity, the halo, and the belt settle into a soft, enduring pattern that supports quiet rather than questions. In the final view, Alnilam settles into a simple role as a steady center inside a quiet frame of gas and dust. The intense physics and long histories already described narrow now to one stable impression. At this distance, the star's light behaves like a calm lantern inside a frosted glass sphere. The lantern is the hot blue-white core. The frosted glass is the ionized shell and the thin dust that softens its glow. Around that shell, the larger cavity stretches an almost spherical hollow, with edges where density rises and light fades. On those edges, fine gradients mark the transition from bright, warm gas into cooler, darker material. Filaments cling to the inner wall like slow streams of smoke that have been frozen in place. Each filament holds subtle ripples in density that may become seeds for later structures. The belt lies across this scene as a straight but delicate bar with Alnitak and Mintaka bracketing Alnilam's central light. That bar anchors the entire region in a simple geometric line that persists through many changing details. Farther out, the Orion arm curves around the galaxy. Within that curve, other clouds clusters and cavities form a loose ring of related activity. Step back still more, and the arm itself becomes one shallow arc in a disk that turns inside a dark halo. From this wide scale, the lantern inside the frosted sphere is almost invisible, yet its influence remains encoded in the gas it stirs and enriches. The single rounded number for this closing view is the remaining lifetime of Alnilam's present phase, about 1 million years. Compared with the age of the galaxy, this span is like a single sustained note held inside a long, quiet song. During that time, the star continues to pour energy into the cavity. The ionized shell remains bright along its inner surface, and the outer wall slowly shifts as gas flows and cools. Some filaments thicken and fragment, others thin and fade into the background medium. Through all these small rearrangements, the overall impression stays consistent. A central blue-white nucleus, a glowing shell, and a soft halo of structured dust surrounding them. There is a clear limit to how much of this future pattern can be traced with confidence. Models of stellar evolution describe the broad path from hot main sequence star to later stages. Models of gas dynamics describe how winds and radiation stir cavities. Yet tiny irregularities in density, magnetic fields and motion accumulate in ways that cannot be predicted detail by detail. The exact placement of each filament and each bright knot in the shell remains uncertain. At the same time, no continuous record spans the full remaining life of the star and the cavity. Observations capture only thin slices in time. Between these slices, the scene may shift in ways that leave no direct trace. The limit sits in both the precision of forecasts and the narrowness of each snapshot. Within those limits, the safest picture is also the calmest. For a long interval on cosmic scales, Alnilam continues to act as a smooth, strong source of light and wind inside Orion. The cavity slowly grows and relaxes. The belt remains recognizably aligned. The arm carries the whole pattern along its orbit without sudden change. The main visual anchor in this final frame is a slow rotation of the frosted sphere around the lantern. As it turns, different sections of the shell present slightly brighter edges or slightly darker lanes. Thin curtains of dust drift across the glowing interior and then move aside again. Nothing abrupt takes place. The changes resemble the motion of shadows across a quiet room during a long afternoon. On the smallest scales near the stellar surface, fusion continues in ordered layers. Particles stream outward in a steady wind. On intermediate scales, inside the cavity, those particles and photons maintain the pressure that keeps the inner walls from collapsing. On larger scales across the Orion arm, combined into contributions from many stars, including Alnilam, help maintain the gentle contrast between active regions and calmer stretches of gas. On the scale of the galaxy and beyond, these details blend into a smooth contribution to overall light and chemical enrichment. The nested scales fit together without strain. One small region holds a highly structured scene. That scene rests inside broader patterns that move more slowly and change more gently. In this settled arrangement, there is no need for new events or dramatic turns. The value lies in the stability itself. The belt continues to mark a simple line in the sky. Within that line, Alnilam continues to act as a luminous heart for the local cloud. Its green-edged blue core shines through dust that softens every sharp feature. The shell around it holds gradients that guide light smoothly outward. Filaments trace quiet paths between dense knots and open spaces. Beyond them, the arms curve and the galaxy's disk offer depth rather than disturbance. Eventually, in far future epochs beyond the scope of this calm picture, Alnilam's structure will change and the lantern will fade. For this closing frame, those distant stages recede into abstraction. The focus remains on the current long plateau where radiation, gas and dust maintain a stable, intricate balance. In that balance, motion and change proceed at a pace that feels almost still. The cavity, the belt and the arm together form a single gentle composition, with Alnilam's light as a quiet central note that continues to shine within the dark, spacious Orion sky.